Yeah. I'm ready.
Okay. Well, welcome everybody. Today we have Zhaojie as our speaker, and he's going to talk about energy transfer and radiation damping for Klein with many entanglement. Please.
Okay. Good afternoon. Thanks for the invitation of Gail and the organizer, and I'm very pleased to present my work here in the PD seminar. And my topic's about the long-time dynamics of the nonlinear Klein-Gordon equation with multiple internal modes in the three dimension. And this is a joint work with Professor Jin Lei in Fudan University and Dr. Jie Liu in the NYU Abu Dhabi. So today my topic will mainly about the Klein-Gordon equation with potential, but I will briefly review the Klein-Gordon equations without potential first. So let's consider this linear Klein-Gordon equation. And the linear Klein-Gordon equation satisfies the classical LP dispersive estimate. So we have this LP prime decay estimate. And we see that the L infinity norm of the solutions satisfy the decay rate of t to the power of minus n over 2. So this is the classical LP dispersive estimate of the Klein-Gordon equation. And for the nonlinear Klein-Gordon equation with pure power nonlinearity, there's also many plenty of these results. So like in the 3D and higher dimension, Klein-Amin and Chatat prove the global well closeness and scattering for the quadratic term. And there's also many other results for the 2D and 1D space. And all of these results, the small solution satisfy the linear decay estimate. So the solution decays at the rate of t to the power of minus n over 2. So this is the nonlinear Klein-Gordon equation without potential. And now we consider the Klein-Gordon equations with potential. So why do we consider this? Because like in the physical setting, there's many Klein-Gordon equations that with potential fields, like with local inhomogeneities, defects, or impurities. And in the mathematical setting, when we study the stability of solitons or kinks, and then we linearized around the soliton or kinks, then we get a Klein-Gordon equation with potential. So let's first see the linear Klein-Gordon equation with potential. So this is a linear Klein-Gordon equation with potential. Then we assume that the potential is smooth and decay fast. In this assumption, the continuous spectrum is from M to infinity. And then the discrete spectrum is made of finite many eigenvalues that is less than M. And all the corresponding eigenfunctions are smooth and exponentially decay. And for every eigenvalue, we can construct a time periodic solution. We assume the eigenvalues are positive, so we can construct a time periodic solutions. Psi equals to r cosine omega t plus theta times phi x, where phi is the eigenfunction. And these time periodic solutions are known as bound state. And on the other hand, if we project the solution to the continuous spectrum, then the solution satisfies a same decay to the free Klein-Gordon equation. So we have uh, and this is proved by using like the wave operator, the boundness of the wave operator, or we can also use the distorted Fourier transform. And so the summary is that for the linear Klein-Gordon equation, for the linear Klein-Gordon equation, the solution can be composed to two parts, the discrete part and the continuous part. The discrete part is made of a linear combination of bound state, so it's time periodic or quasi-periodic, and the continuous spectrum part is behaves like the free Klein-Golden equation, and the decay rate is t to the power of minus n over 2. But how about the nonlinear case? So let's consider a nonlinear Klein-Golden equation with potential that has a pure part nonlinearity. And the global Will-Poseness is well known. So we still have the global Will-Poseness. But what is the long time behavior? So on the one hand, we have a time periodic solution for the linear equation, and we have a scattering part. But in the nonlinear case, these two parts couples together. So we are interested in what is the outcome of this nonlinear coupling. And the general answer to this question is that under some resonance condition, which we also called the Firm's golden rule, the small solution will scatter, but decays in a very slow rate. In other words, the periodic solution, the bound state of the linearized equation, is unstable under the nonlinear perturbations. And the instability mechanism is due to the nonlinear resonance interaction between the bound state and the radiation. And typically, the energy transfers from the bound state to the continuous part, so that all the solutions, the L infinity norm of the solutions decays when t goes to infinity. And we're interested in an accurate description of this dynamics. So for this type of question, we have many related works. So for the nonlinear Klein-Golden equation, the first result is by Siegel in 93. And then an important breakthrough is by Soffer and Weinstein in 99. And then many other results. And there's also a breakthrough result by Lager and Posatteri. They treated the 3D quadratic Klein-Golden equation. And we also have this result for a nonlinear Schrödinger, many results. And this question is actually also closely related to the asymptotic stability of 1D kinks and solitons. Like the very important open question of the asymptotic stability of Pfeiffer model in the 1D scalar field theory. And I believe there's also many like many open problems in this area and many recent results about this. Okay, and then so now go back to our framework. We focus on the 3D cubic case. So the nonlinearity is cubic, and we assume that this linear operator is positive. So there's only internal modes. There's no unstable modes, and we assume that this potential decays very fast and is generic. Generic means there's no threshold resonance. And we assume that the data is always very smooth, very small, and very localized. So the data is sufficiently good. And we need some resonance condition, which is the Firm's golden rule, to ensure the resonance between the internal mode and the continuous spectrum part. So let's first introduce the first breakthrough result by Soffer and Weinstein. In their work, they assume that the operator has only one eigenvalue lying in M over 3 to M, and they assume a certain Firm's golden rule, gamma equals to this inner product, and this inner product is actually non-negative, so they assume that this inner product is non-zero, so makes this positive. And under these assumptions, they prove that the solution can be decomposed into two parts. RT cosine omega t plus theta times phi is the discrete part, the internal mode, and eta is the continuous part. The the internal mode decays at t to the power of minus 1/4, while the continuous part decays at the rate of t to the power of minus 3/4. So we see that in contrast to COM type result, this periodic solution is not exists under the nonlinear Hamiltonian perturbations. And we see that the decay rate of the solution is quite small because of the existence of internal mode, which is much slower compared with the linear dispersive equation, with the linear Klein-Golden equation. And there's energy transform between the internal mode and the continuous mode because the energy is conserved. So the decay of the internal mode implies the energy transfer from the internal mode to the continuous mode. And in their work, they only consider the omega larger than m/3 because their resonance condition requires that 3 omega lies in the continuous spectrum. So after their work, there's some further questions. So first, if B has a small eigenvalue that lying close to 0, less than m/3, then the resonance should be much weaker. So what should we do about this case? And the second case is when the operator has multiple eigenvalues. So and these multiple internal mode may couples together, and which may create different phenomena. So this is the further question. And a related important progress was made by Bambusi and Kukania. They proved that for sufficiently small initial data in the energy space and for some generic nonlinearity, they proved that these solutions are scatters to a linear equation, to the solution of a linear equation. But however, because they deal with the initial data in the energy space, so it is impossible for them to derive the explicit time decay of the solution because the energy is conserved. And they also made the assumption on the nonlinearity. So they made assumption that the nonlinearity should be generic, and it turns out that the cubic nonlinearity is not generic under their definition. So we are also interested about the cubic nonlinearity, the pure power cubic nonlinearity. So we first deal with a single internal mode case when the eigenvalue is close to 0. So we assume that the eigenvalue omega lies between m/n plus 1 to m/2n minus 1, where n can be an arbitrary integer. So when n is large, the omega is very small. And then we assume some resonance condition, gamma doesn't equals to 0. Then we can still derive the decomposition of the solution. Psi equals to the internal mode part and the continual part. And we prove that the internal mode part decays at a time t to the power of minus 1/4n, and the continual part decays at t to the power of minus 3/4n. So when n goes to infinity, the decay rate of the solutions become very, very small. So the resonance coefficient in our generalized Fermi-Golden rule is also some quadratic form. And this quadratic form is ultimately non-negative. So our assumption is assume that this quadratic form is non-zero, which makes it positive. And when we set the capital N equals to 1, then this is become exactly the work of Sofer and Weinstein. And we also prove that our result is sharp, our decay rate is sharp because we also obtain the same lower bound of R, of the internal mode part. And then we continue to consider the multiple internal mode case. So we assume that B can have like n distinct eigenvalues, omega 1, omega 2 to omega n. And then we can also like uh, assume that omega j has multiple has a multidimensional eigenspace, so that one eigenvalue omega j can correspond to many eigenfunctions, phi j1 to phi jlj. And we can also, and for each omega j, we assume that this omega j lies in some interval from m to m over 2nj plus 1 to m over 2nj minus 1. And we need an additional assumption on the omega j, that is the some integer linear combination of omega j is not equals to 0. But is not equals to 0 or m. But this condition is also considered generic because if we fixed a potential v, then this condition holds for like almost every m on the line. So we think this condition is generic. Then we can still write the equation, write the solution into the internal mode part and the continuous part. So here QJK is like the projection, the coefficient after the psi projected to phi jk. So under these assumptions, we can still prove the decay rate of the solution. So here we prove that QJK decays at a rate of t to the power of minus alpha j over 4nn, where alpha j is the minimum of nn over nj to n3. So if we let j equals to n, then alpha n actually equals to 1. So the slowest decay rate of the internal mode is t to the power of minus 1 over 4nn. And we also have the decay rate for the continuous continuous part, and the decay rate is t to the power of minus 3 over 4nn. So this 3 is due to the nonlinear, the cubic nonlinearity. And our Fermi's golden rule becomes a matrix, becomes many matrix. So this T in lambda rho is a semi-positive definite matrix. And we assume that these semi-positive definite matrix are invertible, so that these matrix becomes positive definite. And we also see that alpha n equals to 1, so the decay rate of the whole solution is t to the power of minus 1 over 4nn. And we also prove that our result is sharp in the sense that we obtain the same lower bound of the solution. So now let me briefly explain the proof of our result. So our result was first our proof was first use a refined Birkhoff normal form transformation, which is from the Bambusi and Kukanian. So, but for our setting, for our pure power nonlinearity setting, we need to make a refinement to make this normal form suitable for this pure power. So, to do this normal form transformation, we need to introduce the complex variable Xi, Jk, and F. So Xi, Jk is like the complex variable for the Qjk, where Qjk is the projection of the solution onto some internal mode phi jk, and F is the complex variable of the continuous part of the solution. So after introduce this complex coordinate, the new Hamiltonian becomes H equals to HL plus HP, where HL is the linear Hamiltonian and HP is the nonlinear part. Then the solution can be written in this Hamiltonian equations. Xi jk dot equals to minus I, times partial h partial kcjk bar, and f dot equals minus I partial h partial f bar. So this is the equation for the in the complex coordinate. And then we can perform the normal form transformation under this coordinate. So for each r, we can perform a normal form transformation up to order 2r plus 4. And the Hamiltonian after the normal form looks like HL plus ZR plus RR, where this RR is some error term, so we can omit it. And the ZR is of in the normal form that cannot be canceled by the transformation. So the Z is actually made of two part, Z0 and Z1. Z0 is actually a linear combination of Xi mu times Xi bar mu, where omega dot mu minus mu equals to 0. And so actually this Z0 is like doesn't really help us for the radiation damping, but Z1 is really the resonance term that really makes the internal mode decay. So Z1 is the inner product of G and F, where F is the continuous part of the solution, and G is some nonlinear combination of the internal mode and its coefficient. So here we introduce a resonance set M, so which is combine all the mu and nu that satisfy omega dot nu minus mu is larger than M. So this resonance set actually tells you for which pair of mu nu uh, the internal mode is resonant with the continuous mode. So after this normal form transformation, the solution can be written in this following form: f dot equals to I minus IBF plus G bar and plus an error term, and CJK dot equals to minus I omega J CJK minus I partial CJK bar Z0 plus a resonant term plus an error term. Okay. So let's focus on the equation of CJK because this equation really shows that how the internal mode decays. So the first term on the right-hand side is minus I times omega J times CJK. This is really the phase rotation of the CJK, so it's not contribute to the decay of CJK. And the second term is minus I partial CJK bar Z0. Heuristically, this term also doesn't help to decay the CJK. Um, and but in contrast to the single eigenvalue case, the CJK square, the Poisson bracket of CJK square with the Z0 is not 0. This means that Z0 may affect the norm of CJK square. So this is not good because we don't know how the Z0 will affect the growth or decrease of CJK square. But we observe that if we once combine all the CJK square together with related to the same J, then this whole part has the bracket of this whole part with Z0 is Z0. This means that Z0 has no contribution on the whole part of the sum of the CJK square. And this motivates us to study the new variable called xj, which is just the linear combination of CJK, which is the sum of the CJK square correspond to the same j. So after we introduce this xj, then we can eliminate the contribution of Z0 term so that the equation is like simplified. And we can then do some other simplifications and then substitute the equation of f into CJK. And finally, we can derive the equation of xj. And then here I omit a lot of intermediate steps because the intermediate steps is like to isolate it the resonance term and then to substitute back to the equation of CJK. And it's like lengthy, but to avoid confusing, I omit here. So finally, we get the equation of xj. That is dxj dt equals to minus the sum of lambda j minus rho j times a quadratic term. This quadratic term is made of gamma lambda rho t in lambda rho and gamma bar transpose lambda rho. So here gamma lambda rho is actually a eigenvalue, a vector that made of some xi mu and xi bar nu. And the matrix ET in lambda rho is like the key resonant part that appears in the Fermi-Golden rule. So we will explain this later. So before we explain our Fermi-Golden rule, we need to introduce some resonance sets. So first we have the original resonance set is M, which is all the mu nu that satisfy omega dot nu minus mu larger than M. This is our original resonance set. And then because we introduced the xj, so we also need to introduce the lambda. That is, each lambda is combined with is a pair of lambda and rho. With lambda and the rho is the sum of nu jk and mu jk correspond to the same j. So it's like a reduced resonance set from M. And lambda star is like the minimum set of lambda, so that every element of lambda star is the leading order element of lambda. And because we can define lambda, we can also define m lambda rho. That is, for each lambda and rho, we pick out every mu and nu that correspond to this pair lambda rho. Okay. And so remark, if for every eigenvalue omega 1, omega 2 to omega j, if every eigenvalue is simple, that is, if every eigenvalue has only one eigenfunction, then actually lambda and m is equivalent, and every m lambda rho is just has one element. So this is our Fermi-Golden rule. This matrix T in lambda rho is a semi-positive definite quadratic form. And so our assumption is that this semi-positive definite matrix is invertible, so that it makes it positive definite. And after assume this Fermi-Golden rule, we see that the equation of xj becomes dxj dt equals to minus the sum of lambda j minus rho j c lambda rho x lambda plus rho. So here c lambda rho is just this quadratic form over the x lambda plus rho. And if we assume the Fermi-Golden rule, then this c lambda rho is positive from below. Is bounded positive from below. So we can assume that c lambda is just like equals to 1. We can just assume that. So we now arrive to this equation, dxj dt equals to this part. And the key difficulty in our analysis is the bad resonance. So in our setting, because there's multiple internal modes, and because we treat the pure power nonlinearity. So in our resonance set lambda star, there's some lambda rho, some pair of lambda rho such that lambda j minus rho j is negative. And this is obviously not good because we expect that xj is the coefficient of internal mode. So we expect xj to decay. So we hope that the right-hand side of the equation is negative. So if lambda, for some j, if lambda j minus rho j is like negative, then the minus lambda j minus rho j is positive. And this may imply some kind of growth of xj, which is obviously very bad. So, and we remark here that this reemergence of bad resonance only occurs in the multiple eigenvalue case and may lead to a growth of discrete mode. And at least this possibility is not excluded. And how can we understand this bad resonance? So my understanding is that because we have many internal modes and we have energy transfer between each internal mode and between the internal mode and the continuous spectrum. So I believe it is possible that for some moment that uh, the energy for some xj, the energy of xj received is more than the energy xj sent. So that at some moment, it is possible for xj to growth. So how to deal with this embarrassing bad resonance? So our base idea is that we notice that the total effect is damping-like. So if we times lambda j minus rho j by omega j and sum them together from 1 to n, then by definition, this is larger than n. So the total effect is damping. But we cannot directly sum them together because if we sum all the j together, then this n equations become one equation. And this one equation only reflects the decay rate of the slowest decay rate of the solution. And this is not far from enough to close our estimate because our estimate depend very heavily on the accurate decay rate of the internal mode. So our observation is that we have a renormalized damping mechanism. So we find that we don't need to sum all the j from 1 to n, but in fact, for any k from 1 to n, we just need to sum j from 1 to k. And then we find that omega j times lambda j minus rho j sum from j from 1 to k is also positive. So that motivates us to introduce a new variable called renormalized variable x tilde, with x tilde j equals to the sum of omega kxk, k from 1 to j. And the equation of this xj tilde is better. So if we see the right-hand side of xj tilde, then the right-hand side is strictly negative. And we find that it turns out that the xj tilde seems satisfy the same equation of xj, except that this negative rho j becomes positive rho j. So the xj equation of xj tilde is strictly better than the equation of xj. So this is a schematic diagram of xj and xj tilde. So for xj, the temporary growth is the possibility of temporary growth is not excluded, but xj is bounded by xj tilde, while xj tilde is always decreasing. And another phenomenon that we observed in this multi-internal mode case is that the coupling between the internal mode case may enhance the decay rate of the internal mode. So once we have used the variable of x tilde j, then we find that then if we substitute some certain lambda and rho, then we already can derive the um, decay of xj tilde, which is t to the power of minus 1 over 2 and j. And this decay rate is actually identical to the one eigenvalue case. However, it turns out that this decay rate may not be the optimal decay of xj tilde if in this multi-internal mode case. So let's see this two-state ODE as an example. So this is ODE of x1 and x2. And this is actually a toy model for a two internal mode problem with omega 1 and omega 2 satisfy these conditions. So if omega 1 and omega 2 is distributed uh, in this way, then the corresponding equation for x1, x2 is look like this. And if we ignore the coupling term, x1 square, x2, and x1, x2 fourth, then we see that the decay rate of x1 is t to the power of minus 1/2, and the decay rate of x2 is t to the power of minus 1/4. However, if we take this coupling term into account, then we see that the decay rate of x2 is still t to the power of minus 1/4. But in the equation of x1, we see that actually x1 squared x2 is much larger than x1 cubic. So in the equation of x1, actually the dominant term is minus 2x1 squared x2. And this implies that the decay rate of x1 has at least t to the power of minus 3/4. So if we treat the x1 isolatedly, the decay rate is t to the power of minus 1/2, and if we treat the coupled equation, the decay rate of x1 is t to the power of minus 3/4. So the decay rate of x1 is enhanced by this coupling. But for the general case, it turns out that this the exact decay rate of every single mode is almost impossible to get, because this the accurate decay rate for every single internal mode relies heavily, sensitively on the distribution of omega j, and it also relies heavily on even on the coefficient of this tells us that the exact rate is almost impossible to close our nonlinear estimate. So what our strategy is not to analyze the exact decay rate of every internal mode, but turn to study the decay rate of x lambda rho, x lambda plus rho for lambda rho in the resonance set. So we substitute and get the equation of x lambda plus rho. And then, so this is the equation of x lambda plus rho. This equation is very complicated, but we can simplify it. So because we can take some specific lambda and rho in the resonance set, and we see that the decay of x to the power of lambda plus rho has at least t to the power of minus 2nj plus 1 over 2nj. And this number is already larger than 1, so it's enough for our analysis. And we remark that even that this decay rate for x to the power of lambda plus rho is not optimal, but if we compare this decay rate with the decay rate by the trivial estimate, that is by combining all the decay rate of individual xj together, which is the decay rate in the equation 4, then for some lambda j and rho j, 3 is already is better than the equation of 4 because in the equation of 4, the sum of lambda j plus rho j over 2nj is not always larger than 1. But in the equation of 3, this 2nj plus 1 over 2nj is already larger than 1. So this comparison uh, implies the contribution of the enhanced damping mechanism. And after this enhanced damping mechanism, we also do some nonlinear estimate for the continuous spectrum part, and then we finally can close our estimate. So this is my today's talk. Thank you.
Thank you so much, Georgie, for the nice talk. Are there any questions? Yeah. Maybe we can use the.
What are the assumptions on the initial data?
Oh, I didn't present the assumption the initial data. The initial data should be should be small, localized, like some weighted norm of the initial data is small, and it should be very regular. And if we if we only need to derive the upper bound of the initial data, then this is enough. If we need to derive the lower bound of the equation, then of the solution, then we also need uh, uh, some assumptions on the initial data of every of the initial data projected to every phi jk. So like the initial data of QJK0, we also need some assumption on that, on the size of QJK0. Yeah.
Okay. And I have a second question. Do you see why Bambusi and Cuccagna exclude the cubic case instead you are able to deal with?
Um. Let me. So because in their definition of generic nonlinearity, they assume that beta prime 0 should not be 0. So so they let me think. I mean not beta prime 0. So like they should assume that this cubic nonlinearity should be u cubic plus c1 quartic plus c2 u quintic, and this coefficient in front of the u quartic should not be 0.
Any other question? I do have a question. So in 2D or in lower dimensions, do you expect to have this enhanced damping mechanism also for
The enhanced damping mechanism, I think this enhanced damping mechanism um, also exists in the 1 dimension and 2 dimension, but this still doesn't help us to close the estimate because the enhanced damping mechanism doesn't help us to enhance the damping of the slowest decay rate of this internal mode. So like if we have many internal mode, then the internal mode with higher decay rate can be enhanced the decay rate, but the slowest decay rate internal mode is not enhanced. So the decay rate is still t to the power of -1 over 4n.
I
So
see.
so it doesn't help you to overcome the difficulty we faced in the 1 dimension.
Right. So you did not show us about the control of the PD part. I mean the continuous
Yeah.
part. How do you deal with because you have bad terms there, right? So how do you deal with those terms?
So like in the 3D part, in the 3D case, the pure continuous part is easy to control. Because it's U-cubic, it's actually easy to control. And for the mixed term, like the internal mode plus times the continuous part, this is obtained like using the improve the local decay because we assume the potential is generic, so we have improved local decay. And the improved local decay is like strictly larger than t to the power of -1, so it's integrable. And for the pure power nonlinearity, we use an inductive scheme to prove the decay rate because initially the decay rate is very small, so we use an inductive scheme to close this.
Okay.
Yes, I didn't put here.
So maybe a last one. So what happened if you go back in the first result and have one internal mode and then let's say a threshold resonance
Oh, so
in the spectrum.
if you
So
have threshold resonance,
one
um
internal,
then I'm not sure. Because our control use heavily on the improved local decay to control the the mixed term of internal mode and the continuous mode. So I don't know.
because in the case of resonance, you have some lost, some lock lost in many cases. So and the lock lost, I guess if you have, I mean, let's say that was just a question that I had in mind when you presented the first result, like what will happen if you have, threshold resonance, if you could have still, decay, but like, very slow compared to what you have there.
Um, because I think if we have resonance, then we can close the estimate because the decay rate of the internal mode is already very small. It's one to the even in one eigenvalue case, the decay rate is 1 t to the power of -1/4. So if we don't have improved local decay, then I think the whole estimate cannot be closed.
Right. Okay, if there's no more question online, I see Remy online. Is there any question from online people? No. So let's thank Zhaojie for the nice talk.
Oh, thank you very much for
No
listening.
problem. Right. So right, guess we can chat through emails for the next step at some point. Did you hear? Zhaojie?
Yeah.
Yeah, I guess we can chat, through emails for the next time, and then bye-bye for now.
Yeah. Bye. Thank you very
Yeah,
much.
no
Yeah.
problem.
Bye.
Because
Bye.
that's what's up. Bye-bye.